Select the major product of the following reaction. So if we look at what we have in this reaction, we have a bromine that is directly attached to an alkene. So this is a vinyl halide. We have another alkene. Specifically, we're going to identify this as a terminal alkene, an alkene at the end of the chain. So we have a terminal alkene. And then we've got a palladium catalyst. And we've got triethylamine, which is a base. And so we have two palladium catalyzed reactions that we're going to be looking at. There's many more, but these are only two that we are looking at in this course. And so one is the Suzuki reaction, which we saw in a previous video. So it's reacting a vinyl or an aryl halide with an organoboron reagent. So the boron points you towards Suzuki reaction. And in this reaction, with a vinyl halide and a terminal alkene with the palladium catalyst and base, this is the Heck reaction. So let's look at what is involved in the Heck reaction and then apply it to this particular example. So what you have, if you're looking at a Heck reaction, is you have a halogen that's attached to an sp2 hybridized carbon, so directly attached to the carbon of an alkene, which would be a vinyl halide, or directly attached to the carbon of a benzene ring, which would be an aryl halide. So we have either a vinyl or aryl halide. And then what we react this with is an alkene. And the best sort of alkene for a Heck reaction is a terminal alkene. So that's at the end of the chain. And this group that we've called Z is typically electron withdrawing. And that just helps to make the alkene reactive enough to undergo this reaction. And so what happens in the Heck reaction is you form a new bond. You basically bring together these two pieces. And so this R group ends up bound to the end of the alkene. And specifically what it does, we've got two different hydrogens. It's specifically going to replace the hydrogen that has a trans relationship to that electron withdrawing group. And this is just a steric effect. So it's going to preferentially form the alkene that's less crowded. So you're going to replace the hydrogen that's trans to that electron withdrawing group. So you're going to form as a product, right? So this is from the alkene. You're going to form a new bond to that R group from your vinyl or your aryl halide. So you will form a new trans alkene. So in the case of this example, we just want to locate what we are bringing together. So we have this sp2 hybridized carbon of the vinyl halide, and we want to look to our terminal alkene. We know we're going to form the bond at that terminal carbon, and specifically we're going to want to replace the hydrogen that is trans. So we're forming a new bond right here, and it's going to have a trans relationship to whatever substituent you have on your other carbon atom of the alkene. So if we're drawing this product, I'll start by drawing the alkene actually, and I'll put in that trans framework. So on one side, I'm going to have that ester. So the ester is playing the role of the electron withdrawing group. And then where this hydrogen was, so here's a new bond, and that bond has to go directly to that vinyl carbon atom. Okay, and so we want to look at our options, and we can see that this molecule is actually the same as A, just flipped upside down. And so we would select this one. And notice that we do have that trans orientation of the alkene. And that would be the only thing that would differentiate A from B. So this is the thermodynamic product. It's making it more stable. It's more less sterically hindered.